All right, thanks everyone for sticking around at this late hour here in Singapore, and thanks for everybody joining online. I want to thank the organizers for giving me this opportunity to present some weird work, which has been my pet project for a few months, and it's been a huge pain because it's related to GANs, and whoever has worked with GANs knows that optimization is not very easy. So let me just talk a little bit about the context. So we're talking about unsupervised learning, and I just wanted to make a quick distinction between density estimation and generative modeling. So we have a random variable x distributed some pi of x, which is our true distribution, and we have samples, which is our training data, as we may call it. And then we have some ideas maybe for a model for this data that we have. And in density estimation, we're interested in evaluating, so constructing a model P of x in an explicit form in a way that we can actually evaluate what P of x is for any given x. And in generative modeling, instead, we do this implicitly, and we try to not necessarily construct P of x that we can evaluate, but we're just interested in being able to generate from a P of x that might, again, be defined implicitly. And this is exactly what GANs do, because they don't specifically have an expression for a P of x, but they're able to produce samples. And this work has been really motivated by a series of lectures I've attended at KAUST, where I'm currently based, by Professor Schmid-Huber, who was given this beautiful series of lectures on thoughts of machine learning. And a lot of the ideas in this talk come from sort of this interaction with him. You can see here some samples generated from one of the state-of-the-art GANs, which is a style GAN 2 from the group at NVIDIA. And this is already 6 years old work. And these faces are faces of people that don't exist, right? And this is quite impressive in the sense that as statisticians, these are 1,000 by 1,000 pixels images. So it's a 1 million dimensional generative modeling problem. So these methods are able to generate samples from a very large and unstructured and structured P of x, in the sense large dimensional, again, we're in the millions here, and structured in the sense that there is a lot of work on this so-called manifold hypothesis, where the hypothesis is that a lot of natural looking images actually live on a low dimensional manifold in this very large dimensional space. Of course, GANs are a bit old-fashioned now already, because in machine learning, people are working a lot on diffusion models, and this is also something we've been active in. But the one good thing about GANs is that once you train these models, then generating new images is just as costly as one model evaluation. So that's very cheap compared to diffusion models, where you actually have to solve stochastic differential equations and in lots of dimensions. And it's, I mean, of course, there has been work on trying to ameliorate the cost of doing this, but still, it would be nice if we could revive GANs and make them useful again. And so I asked Google Gemini, to help me to make this talk a bit funnier and more light, given the last talk of a long day here at Basecamp. And so the idea is that in GANs, you sample a batch of, so we can call them latent variables, all right? So we are here, we're statisticians, we can call them like that, Zi, and then for this batch of images, we generate new images from a so-called generator, which is implemented by a neural network here, which is this fgen here, which takes in input these latent variables, and it has parameters, all right, which I denote by W. And then there is a discriminator, which is another neural network, which is trying to classify generated versus true samples. And so in this cartoon here, you see that the generator is this artist with three arms, actually. So if you see here, and it's trying to generate images, and the discriminator is the one that is trying to actually classify fakes from the original data. And so the objective is quite intricate, in the sense that the generator is trying to so the discriminator is trying to minimize its error rate in doing this classification, but actually the generator is the opposite objective of actually maximizing this error rate. And so optimization is very challenging because of this interplay between these two neural networks that have a dialogue in one way. in an antagonist way. And so when I started working on this, I felt when I was looking at implementations online of, how people implement these things, then you realize that it feels like some people just had a bad dream where they magically got all this information about the specific learning rates and architectures that actually work. And if you try to deviate just slightly from these learning rates or ways in which you anneal the learning rates and all these kind of things, then you end up with something which just doesn't optimize. It just breaks down optimization completely. So optimization is very fiddly, and you need very specific hyperparameters to be able to make it work. And this is obviously a major disadvantage of these models, and I believe one of the reasons why a lot of people started moving away from this. But again, because of my interaction with Jürgen, Professor Schmidt-Huber, a Kaust, who has done a lot of work on interpreting GANs as an instantiation of curiosity in a way. So artificial curiosity, so I thought maybe we can start thinking about ways in which we can interpret this in more statistical way. And so I asked Gemini to produce a picture for what a latent variable model could be. And so apparently this guy here is observed data. And these guys here, the little guys here, are the latent factors. The text doesn't make any sense. So if you try to read, there is no sense in what's written there. All right. But the idea, if you think a latent variable model, you have some latent variables, and then you put a prior on these latent variables. And then you have a generator now, which is a deterministic mapping, which takes these latent variables as before, and then and the parameters of this neural network, and it produces input variables. And now, if we are thinking about these models, what kind of likelihood do we have? Well, the likelihood is actually some sort of very degenerate object here, which is a Dirac's delta, where you're only getting infinite likelihood if you're generating from a Zi exactly one Xi that you have in the training set. Otherwise, you get zero. And so this is the kind of likelihood that you're implying when you are thinking about a model like this. And so we're trying to mirror now the construction of the GAN. And now let's take it one step forward and say, okay, what kind of posteriors would we get if we have a likelihood like this? Well, the posterior would be deltas. What kind of posteriors would you want? Would you like that kind of posterior? Not at all, right? So we like posteriors that have something interesting to say about our data. And so here comes the connection with the Bayesian neural networks, which have a long history now. And so in a Bayesian neural network, you take a neural network and you start putting prior distribution over the weights. But now, recent work has pointed to the fact that in order to be expressive in the way we can produce distributions over X, we don't really need to be fully stochastic. So we can be partially stochastic, meaning that even if we are stochastic only about a subset of the weights, we can still approximate any continuous density in the output. And this work by Sharma and others in AI Stats 2023 shows that. And in a way now, what GANs do instead of having randomness in the weights, they put the randomness in the latent variables. And it turns out that these two constructions, actually these three constructions, give you, under certain conditions, they give you already enough flexibility to model any P of X that you want. So this is great for a few reasons. One reason is that we can then establish what are the conditions that we need in order to be able to approximate any continuous densities. And this condition is that you need the dimensionality of the input to be equal to the dimensionality of the output. But in practice, we know that data lives on a manifold in most cases, so we just need less, right? And this is why GANs work. And also, we need enough flexibility. We need to be able to take the stochasticity that we have at the beginning of the network and be able to splash it out in the output in any possible way. And this is how the universal approximation theorem of neural networks comes into play to be able to sort of establish this universal approximation for continuous densities. And so now we are in this position where we have to choose. So what kind of model should we choose among these three possible options? So clearly, partially stochastic is a good idea because we have less work to do as Bayesians, right? And some parameters we optimize, some parameters we treat in our way, like with MCMC, variational, you name it. And GANs, so this is one thing. And so yeah, we talked about the fact that this also gives us an opportunity to then establish a universal approximation. But then this becomes a model selection problem. So because both options are equally good, then which one should we choose? And we are free to say we use a GAN or we use a partial stochastic network. And this is actually work that we did a few years ago when we were talking about Bayesian autoencoders. And so this is some other stuff that we did in the past. But today we focus on this construction of the GANs. And so now this is the more mathsy kind of slide where you can kind of show that if you now think about the marginal likelihood, you can manipulate this marginal likelihood in a way that you can show that the marginal likelihood of these latent variable models are actually a KL objective where you're trying to measure the KL between pi of x, which is a true data distribution, with the p of x that you can produce with your GAN. So essentially, if you're trying to maximize the marginal likelihood of these models, which is optimizing the parameters of your neural network generator, is equivalent to minimizing the KL between your true distribution and the one you produce with the GAN. So now this is, if you're a bit familiar with GANs, you see where I'm going, because now I can replace this KL with whatever I want, maybe, because I don't like KL, I like some other divergences, or maybe I like some other integral probability metrics. And then you can end up with all these formulations where you replace the KL with the Jensen-Shannon divergence, so you get the original GANs formulation, you can replace it with F divergences, you get F GANs, or again, integral probability metrics, so you can end up with Wasserstein GANs and MMD GANs, and you name it. All right. So I took you from on a journey from latent variable models to GANs. But if you're more familiar with GANs, you can think that you can go the other way and say, okay, I have a GAN which has a certain objective. So this is a matching objective between P of X and the one I produce with my GAN. And now this corresponds to some generalized marginal likelihood, okay? And in some cases, maybe this is possible to derive analytically what this marginal likelihood, generalized marginal likelihood would look like. In some other cases, it may not be possible. Okay, but now what's the problem then? Okay, so now we established that GANs optimize some sort of proxy for the marginal likelihood, and they may have enough flexibility to model NP of X. How should we choose the architecture of our GAN? Well, the more complex the architecture is, the more flexibility you have, the easier it's going to be for the model to do the matching of the P of X you have. But this is where the problem is. You may have too much flexibility, and this too much flexibility you pay as overfitting. And how do we counter that? And one simple intuition about this is that imagine any model selection problem you can think of. The easiest one for me is polynomial regression. If you're flexible enough that you can place your, you want to do marginal likelihood optimization, and you're free to move your prior anywhere you want and change the variance as much as you want. So you're so flexible in the prior, and marginal likelihood optimization is going to do the following. It's going to take the prior and going to put it on the maximum likelihood, and it's going to make the variance go to 0. And so you completely negate the effect of Bayes, right? And so your any polynomial order above a certain number is going to fit perfectly your data, and there's no way for you to determine which one is the best polynomial. So how can we gain regularization in a way? And so this is a 2D example, a Gaussian 2D example that illustrates this problem and also maybe offers a solution. So imagine you have Gaussian data in 2D, and I have 3 different models, MLP 0, 1, and 2, and the dimensionality of the input 1, 2, and 10. And so a model with p equal to 1 means that I'm trying to take one latent variable in dimension 1 and map it to the Gaussian. So no matter how complicated the model is, this is never going to obtain a good value of the objective. And you see it here, this red line here. It's not very good for models with p equal to 1. The other models MLP0 is just a linear model. MLP1 is a neural network with one hidden layer. MLP2 is a neural network with two hidden layers. All the others are perfectly capable of obtaining a very good value of the objective at the end of the optimization. But the problem is that these solutions are characterized by one difference, which is key. And the difference is that simpler models are more robust to perturbations. So if I perturb the model around the minimum, and this is what I'm doing here with this alpha, is how much noise I'm adding to the parameters at the end of the optimization. You see that for simple models, nothing really changes in the objective. So these are really flat minima in the loss landscape. Whereas for these models, which are more complicated, as even a small perturbation leads to a very different value in the objective, meaning that we found a solution which was in a very sharp minimum. And so this connection between flat minima, Occam's razor, which is this idea of favoring simpler explanation to our to explain our data, have been talked about a lot in the literature. And so we have two solutions here, two options. One option is to, by construction, enforcing that these models have flat minima. Or the other case is that when, so this is the kind of left side of the picture. On the right side here, we have a loss landscape, which is very complicated. And we may want to favor solutions that are flat, again, because of the issues I talked about before, and also because these solutions are not only simpler, but also the simplest solutions means that they are more compressible, and they're associated with the low description length. And so this is really the plan for the methodology that I'm trying to propose in this work, which is let's regularize, and also let's try to find local minima which are flat, okay? So in terms of regularization, what we can do is one thing which is super simple, which is just relax the likelihood. The likelihood was a delta. Let's make it a Gaussian. And by doing that already, you see that the optimization, which is usually unstable after a certain number of iterations in GANs, already stabilizes that. Another one is to do gradient regularization. This has been talked about a lot in the literature of GANs, and so also this one, this is really the instabilities that you see here in the optimization get fixed up by this gradient regularization. The other idea is to look for flat minima. How do you look for flat minima? Well, one thing is to use small batch sizes. When I was looking at the first implementation I looked up online, I was looking and I was seeing that people use very small batch sizes. And I was like, no, I have a lot of compute. I'm going to use 5,000, as a batch size. The issue with that is that large batch sizes have small variance in the gradients, give you small variance in the gradients, which means that you're very precise in exploring the space. And so you can really end up in this sharp minima very easily. So small batch size is a good thing to regularize. And you can see it in this optimization for a GAN for MNIST. The other thing you can do is to look for for flat minima by using, for example, sharpness-aware minimization. And this is something that also improves optimization considerably. And let's have a look at some results. So this is for Celeb, so it's celebrity faces. So we have that this FID score is a measure of quality. Well, all these three scores are a measure of quality of these images that you can generate. You can see that already by adding, so doing this likelihood regularization where we add some noise to the generation process, we obtain an improvement. And it's crazy, like nobody in GANs literature would think about adding noise to the generator. Why? Because they think, well, now the generated images are noisy, so the discriminator will have an easy time to classify them. But actually, if we understand Bayes and understand marginal likelihoods, this is a perfectly sensible thing to do. And of course, when I generate my images at the end, I don't generate them with this noise, right? So they look clean. And this is like latent variables and epistemic aleatoric uncertainties. It all makes sense. And so this pattern is kind of you can see even with largest batch size here, you see that you get an improvement in FID score here just by adding noise, okay, which is very simple. So here are some uncurated samples from the celebrated data set. The samples are here. You see that they don't look that great either, even the data themselves. And so these are the uncurated samples that I generated from these two models here. Okay, so another thing is about compression. I think for the interest of time, I will just go quickly here. So just to say that what I tried to do was to say, well, what if I compress the models now? So I get them from double precision to integer. I compress the weights, okay? So this is a form of perturbation, and I want to see how much I lose by doing this. And so here in percentage, you see how much performance you lose by doing this. And so the bottom line is that if you use Adam here, on average, you get slightly less in terms of degradation in performance. Okay, so I just wanted to conclude here so I can take questions. So this work is really in the direction of trying to understand GANs and hopefully get some improvements through Bayesian principles. And I was quite excited at the beginning of this project because I thought that model selection would allow me to do architecture search, which is in the end a big problem, right? So how do you choose the architecture for any neural network in your whatever problem you have? And I thought that thanks to this, because we have an objective which is already proxy for marginal likelihood for model selection, that then you could just do architecture search for this. And I think it's something I would like to try. We haven't done it yet, but it's something that is in the plans. And there are some works, recent works that actually apply sparsity and architecture search in some way by doing sparsity, which use exactly the objective of the GAN. And that's a perfectly valid thing to do. Most people, when they do architecture search, they have to have a validation set against which they have to compare. Nobody would do model selection on their loss. But because of this loss is a marginal likelihood loss, it's a valid thing to do. And so I think that something that should be explored. Of course, all the images I've generated in Gemini are text to image, right? So we should definitely work more if we want to do something interesting with GANs to push them to be multimodal, which for us would mean multi-source, right? So in the literature of machine learning, multimodal means multiple sources of information, right? So the paper is coming soon. We are running some big experiments on these larger images, and I thank you for your attention.